and welcome back to Teacher Gimble's channel. Today we're going to be going over Illustrative Math, Algebra 2, Unit 1, Lesson 10 Practice. If you like this video, please make sure to like and subscribe. I think the button's right over there. Now, I took a few weeks off from making these videos just because I was doing some traveling, and even when I came back to these videos, I needed to take a second to resituate myself with the notation to become familiar with it. All of the content, and especially the content in this unit, uses specific notation that you have to be very comfortable with for these questions to make sense. So if you're not fully comfortable with this content, I recommend you going back and looking at some of the previous lessons before jumping into this one. Let's get started. Problem 1. A sequence is defined by f of 0 is equal to 3. F of n, so n represents the number term in our sequence. So we're going to have the first term, the second term, the third term, the fourth term, is equal to 2 times f of n minus 1. This right here is always, if you recall, just the previous term. So it's going to be 2 times the previous term for n is greater than or equal to 1. Write a definition for the nth term of f. So let's get started. My first term, so that's going to be my first, my second, my third term. Second, third, fourth, ... Let's figure it out. It's going to be 2 times the previous term. 2 times the previous term is 3. My second term is going to be 2 times the previous term, which is this. So 2 times 3. My third term is going to be 2 times the previous term. So 2 times this whole dude. 2 times 2 times 3. My fourth term is going to be 2 times this whole dude, which is 2 times 2 times 2 times 2 times 3. And if you notice, each time we're just multiplying the previous term by 2. So how do we write this out in terms of a function? F of n is going to equal 3, because that 3 never ever goes anywhere, times 2 to whichever number term we're on. And we're done. And this is how we generally do most geometric sequences. I like thinking about it like this in case I need to go back and review and think about why this is the case. Because if I know the why, then determining kind of the process or the formula is always going to be easier for me. Take a second to pause this video if you need to go over it again before moving on to question 2. Problem 2. A geometric sequence starts 20, 60, ... So because it's geometric, we know we're multiplying each term by something. To get from 20 to 60, I'm multiplying by 3. So I'm just writing that down immediately. Define g recursively and for the nth term. So recursively means we're defining it by the previous term. So if we're starting at 20, so we're going to say g of n, this is going to equal to our first term, or a 0th term, is going to be 20. And then g of n is going to be what we're multiplying it times the previous term. And that's how we get it, because it's going to be the previous term multiplied by 3 gets us the next term. The previous term multiplied by 3 to get our next term would multiply it by 3, and we'd get us 180. And that's what this says over here. Now, if we want to flip this into function notation for the nth term, what we're going to say is this 3 is never going anywhere, but we're going to keep multiplying it. Actually, the 3 actually does. Sorry, that was my bad. Our first term, we start with our first term, which is 20, and then we multiply it by 3 as many terms as we want. So if we want to multiply it by 3 10 times to get the 10th term in the sequence, we do 20 times 3 to the 10th power. So again, because this is a geometric function, we're going to be looking at this formula for most of these questions. And what we're noticing is the initial value, or the first term, is this constant. This is going to be your rate of change, and your n goes up in an exponent. So we're going to keep seeing this pattern over and over again. Let's go to the next question. A geometric sequence g starts at 500. So our initial term is 500 and has a growth factor of 0.6. Sketch a graph of g showing the first 5 terms. So we know we have 0, we have 1, 2, 3, 4, 5. And the highest value, we're going up to 500. Now, I know that our values are getting smaller because when I multiply a number by 0.06, it's going to get smaller, which is why I started with my highest at 500, and I'm going down like that. So I start at 500. My initial term is 500. My next term is going to be 500 times 0.6. Now, because I'm sketching, instead of doing a calculator, I could do 500 times 0.6 in my handy dandy calculator, but 0.6 is a little more than half. So a little more than half for my next term is going to be a little above 250. And a little more than half of 250 is going to be 130 something or 120 something. That's going to go right about there. And a little more half than that is going to go right about over there. And a little more than half than this is going to go right about over there, right about over there. And because it's a geometric sequence, I see that it's a curvy dude. And that's how I know that I did this correctly. Now, if you wanted to create a table, you could start with 500 is your first term. Your next term is going to be 500 times 0.06. Your next term is going to be whatever this is, so 500 times 0.06 times 0.06, and you could go ahead and you could fill out your terms of values just like that. However, because I'm sketching, I kind of just do this in my head to get a general sense of the pattern, which is what I like to do because it helps me double check that my intuition is correct and also saves me time when I'm doing a sketch. Let's go on to problem number 4. An arithmetic sequence, so we're adding here or subtracting, has a value a of 1 is equal to 4. So my first term is 4. A of 2 is equal to 16. My next term is 16, which I immediately look at. I know that I add 12 to each term. So 16 plus 12 is going to be 28, plus 12 is going to be 40, ... Explain or show how to find the value of A of 15. So let's take a second and we're going to write a function for this value. So we want to say A of 15. Well, let's think of A of n. We are always going to start with a 4 because that's our initial value. Then we're going to add 12 to get to our next term. But to get to each following term, we're just going to add 12 as many times as we need. So I'm going to say we're going to add 12 n times to get to that term that we want. Now, if we want to find A of 15, we're going to say A of 15 is going to equal 4 plus 12 15 times. Because to get to the 15th term, we're going to be adding 12 15 times. And that gets us to the correct answer. Pause this video if you need a second to go over it, because that was our first arithmetic sequence that we've dealt with in this problem set. And I realized that I just made a quick mistake here, because we're not given A of 0 is equal to 4. We're given A of 1 is equal to 4. So when we're looking at the second term of our sequence, we're actually not looking at adding 12 twice. For our second term, we added 12 once. So let's edit this function over here. Now, making a mistake is a part of mathematics, and that's okay. So for our second term, we add 12 once. For our third term, we've added 12 twice. So instead of starting with n, we're actually going to have n minus 1 as part of our formula. So we're going to get rid of that right there, and that's just going to be 15 minus 1. And this right here gets us the correct function. So we always need to take a second and double check our answers and to look it over, because we do make mistakes, and I make mistakes like anybody else does. And I do these problem sets with you at the same time. So I apologize for any mistakes, but let's go on to problem number 4. A geometric sequence has g of 0 is equal to 4. So my initial value is equal to 4. And g of 1 is equal to 16. So it's a geometric sequence. I know that I'm multiplying by 4. And I know I'm multiplying because it's a geometric sequence. Explain or show how to find the value of g of 15. So we've just done a bunch of geometric sequence questions. So let's go ahead and think about this. We know we start with our initial value, which is going to be 4. And that guy never changes. And then we're going to multiply it by 4. And then it's going to be dependent on the number of terms. Now, real quick, I'm thinking my first term is going to be 16. So when I plug in 1 times 4, 4 to the first power is 4, times 4 is 16. So this is correct. We don't have to put n minus 1 because we're given g of 0 and not the first term of the sequence. So we have to be careful thinking about what we're given. Now, if we want g of 15, we would say g of 15 is equal 4 times 4 to the 15th power. And we're done. So that's how we define our geometric sequence in this case. You could put this all into a handy dandy calculator, but this is just going to get you a really big number. So go ahead and do that on your own time if you would like to. Problem 15. Complete the table with the area of a piece of paper in square inches that is folded in half n times. So I'm taking a piece of paper, which looks like this, and I'm going to fold it in half. So after one fold, well, 0 folds, it looks like this. After one fold, it's going to look like this. After 2 folds, it's going to look like this. So I notice immediately that the area is getting smaller, and logically I'm saying, okay, the area is getting smaller by 1/2 each time. At this point, I can't really fold it anymore. So we're going to complete the table. If we start with 96, well, after one fold, that's going to cut in half. So half of 96 is 48. After 2 folds, the 48 gets cut in half. Half of 48 is 24. After 3 folds, half of 24 is 12. And we've completed the table. Define a for the nth term. So our initial value is 96. So we always start with 96. And then we're going to multiply by half, or 0.5. I always put my decimals in parentheses, for as many terms. So the first term we've multiplied by 0.5 once, and the second term we multiplied by it twice, which means we can stick the n up there, and it doesn't have to be an n minus 1. So we've defined a for the nth term. We're done. 3. What is a reasonable domain for your function? Explain how you know. So domain is a reasonable number of values for what we're plugging into our function. Now, when I took my piece of paper, I think I folded it 1, 2, 3, 4. I guess I could do it 5 or 6 times, but after that, I can't fold it anymore. So I would say a domain would be n is less than or equal to, let's say 8 for somebody who's really strong and can fold it really tight. But after that point, it gets too hard to fold, so our domain becomes an unreasonable amount. Now, if the paper was bigger, it might be different, but it says 96 square inches, which I think is 8 by 13 is 96 square inches. I'm not sure. You can go ahead and do some research on that on your own. I'm going on to the next question. Problem 6. Here is a growing pattern. Describe how the number of dots increase from stage 1 to stage 3. So there's 2 dots here. There's 4 dots here. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 dots there. So it gets multiplied by 2 each time. I've described it. Write a definition for a sequence D so that D is the number of dots in stage n. So let's see. If D represents the number of dots, now I see that I'm multiplying by 2, so it's a geometric sequence. My initial term is 2, and for each additional term, it's going to be multiplied by 2. My second term is multiplied by 2 once, so it's going to be n minus 1. My third term is multiplied by 2 twice. So because this is our initial term, in this case is g of 1 and not g of 0, we're going to put that n minus 1 to define this. So that's how we define the number of dots in stage n. Now, because our base value is the same, and if you're not really comfortable with exponents, be careful here. This is technically 2 to the 1 plus 2 to the n minus 1. We could rewrite this as 2 to the n because we add the 1 and the negative 1, and that gets our value. But do this in the best way that is intuitive to you, because both of these answers say the same thing. And for me, because I'm starting with g of 1, I like to write it in this notation over here. And this only simplifies is because both of our base values are 2, so it works. Now, is D a geometric sequence or an arithmetic sequence or neither? Explain how you know. Well, we're multiplying by 2 each time. And we've gone over this in every single lesson for the past 10 lessons. So it's a geometric sequence. All right, let's go on to the next question. Problem number 7. A paperclip weighs 0.05 grams and an empty envelope weighs 6.75 grams. Hand adds paperclips one at a time to an empty envelope. Complete the table with the weight of the envelope, W of n, in grams after n paperclips have been added. Let's see. So we start with an empty envelope. So with no paperclips, our envelope weighs 6.75 grams. Now, each paperclip weighs 0.5 grams, so after we add 1, we're going to add 0.5 grams, which gets us 7.25. We add another 0.5 grams for second paperclip, we get 7.75. We add another 0.05, we get 8.25. And if you're not comfortable with adding decimals like this, use your handy dandy calculator. Let's erase this so our table looks a little cleaner. So we added 0.5. Now we're adding the same value to each term, which tells me immediately this is an arithmetic sequence. Now, what we're plugging in is n. This represents number of paper clips. So it's important to think in words of what we're talking about. So when we have question 2, does W.1025 make sense? Well, unless you have a quarter paperclip or a 0.25 paperclip, it does not make sense because we're adding paper clips one at a time in terms of whole paper clips. So a decimal number of paper clips don't make sense. So no, it does not make sense. And that is the end of our problem set. If you like this video, please make sure to like and subscribe. I think the button's all the way down there somewhere. Someday I'm going to figure out this video. And I will continue to make more of these. Put questions in the comments. And I look forward to seeing you in the next one. Bye.